start by the first speaker, Roman Makarov. He is a junior researcher at the Laboratory of Neurobiology at Kazan Federal University in Russia. And I've been personally always fascinated by the development of the brain. But today he's talking about another developments, about development of the auditory system. And in rat, especially, this is less known than the auditory, that the visual system. Roman is talking today about the development of hearing in the neonatal rats, cortical response to air and bone conducted sounds. Thank you, Roman, for joining us, and we are looking for your talk.
Thank you, Roozbeh. Hello, everyone.
Sorry, Roman, also, can you turn on your video?
I can't turn it because it doesn't work.
Okay, no worries. Yeah.
Okay. Okay, I'll just share my screen. Let's try it. Okay, can you see my screen?
Yes.
Okay, great. So today I'm going to talk about the early postnatal development of the rat auditory system, and specifically about the cortical responses to bone-conducted sound. So what is special about bone-conducted sound? As we know, rats are altricial animals, meaning that they can't hear after birth during about 2 weeks. But morphological studies suggest that this inability to hear is mainly due to the immaturity of the conductive structures of the outer and middle ear. It was shown that bone-conducted sound, which bypasses the outer and middle ear, can evoke auditory brainstem responses already at the 7th postnatal day. So these responses are the earliest auditory evoked responses, and we can use them to study the early cortical development. So in this work, we were aiming to characterize the spatial and temporal characteristics and developmental profile of these responses, and we used micro-ECoG electrodes. So here you can see the electrode array with 60 electrodes in total. And also, along with the recordings from the cortical surface, we used silicone probes to record the activity throughout the depth of the cortex. And we inserted these probes in the special openings. So here you can see the cortical response to bone-conducted sound on each of these 60 electrodes. And here you see the superimposed traces, and the trace with the maximum amplitude is shown here in black. And you also can see the initial positive component of the response and late negative component. By averaging the activity within several milliseconds around the peak values, we can obtain such spatial maps to understand the spatial organization of these responses. And also using the intracortical recordings, we can relate the superficial signals to the activity within the cortex. And for example, here you can see that the positive component is related to the earliest sync and to the maximum firing rate in the thalamus-recipient layers, meaning that this activity comes from the thalamus to the cortex. And the negative component is related to the activity in the superficial layers. So it probably means that the activity can propagate within the cortex. And I would like to show you a short video. So you can see here the emergence of the positive peak and now the negative peak. And you also can see that it spreads down here in the caudolateral direction, which is consistent with the previous results in adult animals, where the activity can propagate within the isofrequency stripes. So these results are quite similar. Okay, next we analyzed the development of these responses, and you can see here the responses on different ages, and you can see how their temporal characteristics changed with age. For example, latencies and delay between positive and negative components, but their spatial characteristics were not dependent on age. And here you can see the distribution of locations of negative peaks relatively to the positive peak, this orange dot. So they are located caudolaterally. And also we checked if these responses are indeed of the auditory nature. To do so, we compared them with responses to electrical stimulation of subcortical structures. For example, stimulation of the cochlea. So you can see here that the pattern of activation is quite similar. And the same holds for the stimulation of the inferior colliculus, which is auditory midbrain. So responses are approximately at the same place. And also after the onset of hearing, we were able to obtain responses in the similar location, responses to the air-conducted sound. And all these results confirm the auditory nature of these responses. And also they were eliminated by the cochlea ablation, bilateral ablation. So these cortical responses have indeed cochlear origin. So finally, we compared different developmental events, and we provide here the timeline of auditory system development, combining previously known results from morphological studies and from studies, for example, spontaneous activity with our data. And we can divide 3 periods of development. The initial period of absolute deafness, then the latent hearing when there are no responses to normal environmental sounds, but it is still possible to evoke auditory responses in the cortex using bone-conducted sound, for example. And after that, at the end of the second postnatal week, we see the onset of normal hearing, as we usually think about it. And another interesting thing was that this developmental timeline is quite similar to the development of the visual system. In the visual system, first responses can be also obtained from the 8th postnatal day, and there is a significant change at around the end of the second postnatal week between the activity profiles. Overall, this system demonstrates striking similarities in their development. So to summarize, we found that bone-conducted sound evokes thalamus-mediated cortical responses from P8. We found that a positive component represents thalamic input and negative component intracortical propagation. And we confirmed the auditory nature of these responses and found the striking similarities between auditory and visual system development. So thank you for your attention. And also, I'd like to thank my colleagues.
Thank you, Roman. Thank you so much.
Thank you. Yeah. If there are any questions, I'm ready to.
Yes, if you have a question, post on question, I can read the question. Thank you so much for interesting study on the hearing. How big is this bump that you're showing on the slides compared to the size of the single neuron in the auditory cortex?
It is mesoscale imaging, so we cover quite large area. For example, here you can see the scale bar is about 400 microns. So the overall area is several millimeters.
Oh, so it's quite big. It's like,
yeah. So we can see here the entire auditory cortex and some adjustment regions as well.
Right, since in visual system, like for example, if you see the Starbucks neurons, like they develop, the size dramatically change over the P0 to P10, P11. And I believe it's supposed to be the same in auditory.
Yeah, so probably on different scale, we will see different pattern.
Awesome. Thank you a lot, Roman.
Thank you.
That was great talk. I want to